In the vast architecture of our solar system, every planet plays a role. Mercury races closest to the Sun. Earth carries oceans and life. Saturn shines with its magnificent rings. But far beyond the inner planets lies a giant that quietly shapes the destiny of the entire system, Jupiter, the largest planet in our solar system. A world so massive that it contains more than twice the mass of all the other planets combined. With its enormous gravity, Jupiter acts like a cosmic guardian, pulling comets, capturing asteroids, and influencing the orbits of nearly everything around it. For billions of years, Jupiter has helped maintain the delicate balance of our planetary neighborhood. But imagine something impossible for a moment. Imagine that Jupiter suddenly disappeared. No explosion, no warning, just gone. What would happen to the asteroid belt? Would Earth become more vulnerable to catastrophic impacts? Would the orbits of the planets slowly begin to change? And could the disappearance of Jupiter eventually destabilize the entire solar system? Tonight, we explore one of the most fascinating thought experiments in astronomy. What would happen if the largest planet in our solar system suddenly vanished? The giant of the solar system. To understand what would happen if Jupiter disappeared, we first need to understand just how important this planet truly is. Jupiter is not simply another world orbiting the Sun. It is the giant of our solar system. With a diameter of nearly 143,000 kilometers, Jupiter is more than 11 times wider than Earth. You could fit over 1,300 Earths inside Jupiter. Its mass is even more astonishing. Jupiter contains over twice the mass of all the other planets combined. This enormous size gives Jupiter an incredibly powerful gravitational field, and that gravity influences everything around it, from nearby asteroids to distant comets to the orbits of other planets. In many ways, Jupiter acts like the architect of the solar system. A massive gravitational anchor helping shape the structure of our cosmic neighborhood. A failed star. Because Jupiter is so large, scientists sometimes describe it as a failed star. This idea might sound dramatic, but there is some truth behind it. Stars form when enormous clouds of gas collapse under gravity. If enough mass gathers together, the pressure and temperature at the core become high enough to trigger nuclear fusion. Fusion is the process that powers stars like our Sun. It converts hydrogen into helium and releases enormous amounts of energy. Jupiter is made mostly of hydrogen and helium, just like the Sun. But Jupiter simply never became massive enough to ignite fusion. If Jupiter had been about 80 times more massive, it could have become a small type of star known as a brown dwarf. Instead, it remained a planet. But even without fusion, Jupiter still behaves very differently from rocky worlds like Earth or Mars. A world of storms, Jupiter is a gas giant. It has no solid surface like Earth. Instead, it is made mostly of thick layers of gas, swirling around a dense core deep inside the planet. Its atmosphere is filled with enormous storms, powerful winds, and colorful cloud bands. Some of these storms are so large that they could swallow entire planets. The most famous storm on Jupiter is the Great Red Spot. This enormous hurricane-like vortex has been raging for more than 300 years. It is so large that Earth could fit inside it. Winds inside this storm reach speeds of over 400 kilometers per hour. And yet, the Great Red Spot is only one example of Jupiter's violent weather. Across the planet's atmosphere, countless storms form, merge, and disappear. The entire planet is constantly in motion. Jupiter's enormous gravity, but the true importance of Jupiter lies not in its storms. It lies in its gravity. Jupiter's gravitational pull extends across vast distances. It affects objects throughout the solar system. One of the most important regions influenced by Jupiter is the asteroid belt. This belt lies between the orbits of Mars and Jupiter. It contains millions of rocky objects, ranging in size from tiny pebbles to dwarf planets hundreds of kilometers wide. At first glance, the asteroid belt might appear to be a dense ring of rocks, but in reality, most asteroids are separated by enormous distances, and the reason the belt never formed into a full planet is largely because of Jupiter's gravity. As the early solar system formed billions of years ago, Jupiter's gravitational influence constantly disturbed the orbits of these rocky bodies. Instead of merging together into a planet, they remained scattered. In this way, Jupiter shaped the structure of the inner solar system. The cosmic shield Jupiter may also play another important role. It may act as a cosmic shield for Earth. Throughout the solar system, countless comets and asteroids travel along unpredictable paths. Some originate from distant regions like the Kuiper Belt or the Oort Cloud. These icy bodies occasionally drift toward the inner solar system. If they collide with planets, the results can be catastrophic. Scientists believe that an asteroid impact helped cause the extinction of the dinosaurs 66 million years ago. But Jupiter's enormous gravity often captures or deflects these dangerous objects before they reach the inner planets. One dramatic example occurred in 1994. A comet known as Shoemaker-Levy 9 broke apart and crashed directly into Jupiter. Astronomers watched as massive explosions erupted in Jupiter's atmosphere. Some of the impact scars were larger than Earth itself. If that comet had struck our planet instead, the consequences could have been devastating. Events like this demonstrate how Jupiter can act like a gravitational vacuum cleaner, pulling dangerous objects away from the inner solar system. A system of moons. Jupiter's gravitational dominance is also visible in its vast system of moons. The planet has more than 90 known moons. Some are small and irregular, captured asteroids pulled in by Jupiter's gravity. Others are enormous worlds in their own right. The four largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons. They were first observed by Galileo Galilei in 1610. These moons are fascinating worlds with unique environments. Io is the most volcanically active body in the entire solar system. Its surface is covered with hundreds of erupting volcanoes, powered by tidal forces from Jupiter's gravity. Europa hides a vast ocean beneath its icy surface. Scientists believe this ocean may contain more water than all of Earth's oceans combined. Because of this, Europa is considered one of the most promising places in the solar system to search for extraterrestrial life. Ganymede, the largest moon, is even bigger than the planet Mercury. It possesses its own magnetic field. And Callisto preserves one of the most ancient cratered surfaces in the solar system. All of these worlds exist because of Jupiter's powerful gravity. They orbit the giant planet in a complex gravitational dance that has lasted billions of years. The balance of the solar system. When scientists study the motion of planets, they often describe the solar system as a delicate gravitational balance. Every planet pulls on every other planet. These forces constantly influence their orbits, but because Jupiter is so massive, its influence is far greater than any other planet except the Sun. Jupiter's gravity helps stabilize the orbits of nearby planets. It shapes the distribution of asteroids. It redirects comets, and it affects the long-term dynamics of the entire solar system. In other words, Jupiter is not just another planet. It is one of the main forces shaping the architecture of our planetary system. The question: so what would happen if Jupiter suddenly disappeared? If this enormous gravitational giant were removed from the solar system, the balance that has existed for billions of years would instantly begin to change. Asteroids would drift into new orbits. Comets might travel deeper into the inner solar system. The motion of planets could slowly begin to shift. At first, these changes might appear subtle, but over millions or billions of years, the consequences could become dramatic. And in the next chapter, we will explore the first place where the effects would appear, the region of space that Jupiter controls more than any other, the asteroid belt, and what might happen if its guardian suddenly vanished. Chaos in the asteroid belt. To understand the first major consequences of Jupiter disappearing, we must travel to a region of space located between the orbits of Mars and Jupiter. This region is known as the asteroid belt. At a first glance, the asteroid belt might sound like a dense field of tumbling rocks, constantly colliding with one another. Movies often depict it as a dangerous maze where spacecraft must carefully dodge incoming asteroids, but the reality is very different. The asteroid belt is incredibly vast. Most asteroids are separated by millions of kilometers. A spacecraft could pass through the belt without ever coming close to a single asteroid. Yet despite this enormous distance between objects, the asteroid belt remains a fascinating relic of the early solar system, and its structure exists largely because of Jupiter. The birth of the asteroid belt. About 4.6 billion years ago, the solar system began forming from a giant cloud of gas and dust. As this cloud collapsed under gravity, a rotating disk formed around the young sun. Within this disk, tiny grains of dust collided and stuck together. Over time, these grains grew into rocks. Rocks became larger bodies called planetesimals. Eventually, some of these objects grew large enough to become full planets. This process created the planets we know today. But something unusual happened in the region between Mars and Jupiter. Instead of forming a single planet, this area remained filled with countless smaller bodies. The reason lies in Jupiter's immense gravity. Jupiter's gravitational disturbance. As Jupiter formed in the outer solar system, it quickly became enormous. Its powerful gravity began influencing nearby regions of the protoplanetary disk. Whenever small, rocky bodies in the asteroid belt region tried to merge together, Jupiter's gravity disturbed their orbits. These disturbances caused the objects to move faster and collide more violently. Instead of gently sticking together and forming a planet, the collisions shattered them apart. Over millions of years, this process prevented the formation of a large world. What remained was a scattered population of rocky objects. These became the asteroids we see today. In other words, the asteroid belt is essentially a planet that never formed. Orbital resonances. Jupiter's influence over the asteroid belt goes even deeper. Because Jupiter is so massive, its gravity creates regions of orbital instability, known as resonances. A resonance occurs when an asteroid's orbital period becomes a simple fraction of Jupiter's orbit. For example, if an asteroid orbits the Sun exactly 3 times for every 1 orbit of Jupiter, it is said to be in a 3-to-1 resonance. These resonances create powerful gravitational effects. Asteroids in these regions experience repeated gravitational tugs from Jupiter. Over time, these tugs alter their orbits. Many are eventually ejected from the asteroid belt entirely. Others are pushed into new paths that may cross the orbits of planets. These resonance gaps are visible in the asteroid belt today. They are known as Kirkwood gaps, named after the astronomer who first identified them. These gaps are direct evidence of Jupiter's gravitational dominance. Nakarku-1. What happens if Jupiter disappears? Now, imagine that Jupiter suddenly vanishes. Its enormous gravitational pull disappears instantly. The consequences for the asteroid belt would begin almost immediately. Without Jupiter's stabilizing influence, the delicate gravitational balance of the asteroid belt would change. Some asteroids that were once locked into stable resonances would suddenly find themselves free. Their orbits could begin drifting slowly over time. Other asteroids that had been prevented from entering certain regions of space might begin migrating inward. Gradually, the asteroid belt would become more chaotic, but the most important change would involve near-Earth objects, asteroids on the move. Many asteroids currently remain trapped in relatively stable orbits within the belt. Jupiter's gravity constantly nudges these objects, but in predictable ways. If Jupiter disappeared, these orbital patterns would slowly change. Some asteroids would begin drifting inward toward the inner solar system. Others would move outward into deep space. Over long periods of time, millions of years, the number of asteroids crossing the orbits of inner planets could increase. This means more potential asteroid encounters with Earth, Mars, and Venus. However, the situation is more complicated than it might seem. Jupiter does not only protect the inner solar system. In some cases, Jupiter's gravity actually sends asteroids toward the inner planets, so removing Jupiter might reduce some impacts while increasing others. Scientists still debate exactly how this balance would shift. But one thing is certain: the asteroid belt would no longer behave the way it does today. The long-term evolution. Over tens of millions of years, the asteroid belt might slowly begin changing shape. Without Jupiter constantly stirring it, collisions between asteroids could become less energetic. Some objects might finally merge together. Larger bodies could begin forming again. It is even possible that, given enough time, the asteroid belt could eventually form a small planet. But this process would take an extremely long time. And the inner solar system would likely experience a period of increased instability first. Some asteroids could be thrown onto unpredictable paths. Others might collide with one another, creating fragments that scatter across space. Gradually, the asteroid belt could evolve into something very different from what we see today. Dr. Sue and Earth's safety. One of the biggest questions is how this change would affect Earth. Asteroid impacts have shaped our planet's history many times. Large impacts can trigger global climate changes. They can reshape continents and oceans. And, in extreme cases, they can cause mass extinctions. Jupiter currently captures or deflects many large comets before they reach the inner solar system. Without Jupiter, some of these icy visitors might travel farther inward. Over millions of years, this could increase the likelihood of large impacts on Earth. However, Jupiter also sends some asteroids inward through gravitational resonances. Without those resonances, some dangerous asteroids might never reach Earth, so the true effect remains uncertain. The solar system is a complex gravitational system, and removing its largest planet would produce unpredictable consequences. A slow transformation. The disappearance of Jupiter would not cause immediate chaos across the solar system. Planets would not suddenly collide. Asteroids would not instantly rain down on Earth. Instead, the changes would unfold gradually, year by year, century by century, million year by million year. The asteroid belt would slowly reorganize itself. Orbits would shift. Collisions would reshape the population of rocky bodies, and the inner solar system might eventually experience a new pattern of asteroid activity. But the asteroid belt is only one region influenced by Jupiter. Far beyond it lies an even more distant reservoir of icy objects, a place where Jupiter's gravitational reach helps control the motion of countless comets. And if Jupiter disappeared, those comets might begin a journey toward the inner solar system. In the next chapter, we will explore what could happen to these distant travelers, and how the disappearance of Jupiter might unleash a wave of long-period comets toward the planets. The Comet Highway. Far beyond the asteroid belt lies a much colder and more mysterious region of the solar system, a vast domain filled not with rocky debris, but with frozen worlds made of ice, dust, and ancient material left over from the birth of the planets. These icy bodies are the comets. Unlike asteroids, which mostly remain confined to the region between Mars and Jupiter, comets travel enormous distances. Some originate from a region beyond Neptune called the Kuiper Belt. Others come from an even more distant structure known as the Oort Cloud. Together, these distant reservoirs contain trillions of icy objects. Most of them remain frozen in darkness, orbiting the sun far from the warmth of the inner solar system. But occasionally, something disturbs their paths. And when that happens, these icy bodies can begin long journeys toward the sun, journeys that may bring them close to Earth. The Kuiper Belt. The Kuiper Belt lies just beyond Neptune's orbit. It stretches from about 30 to 50 astronomical units from the Sun. An astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers. This means the Kuiper Belt begins roughly 4.5 billion kilometers away from the Sun. Within this distant ring exist countless icy worlds. Some are small comet-like bodies. Others are large enough to be considered dwarf planets. One of the most famous objects in the Kuiper belt is Pluto. For many years, Pluto was considered the ninth planet, but astronomers later discovered many similar objects in the Kuiper belt. Because of this, Pluto was reclassified as a dwarf planet in 2006. Despite their distance from the Sun, these icy objects are not completely isolated. Their orbits are strongly influenced by the giant planets, especially Neptune and Jupiter. The Oort Cloud. Even farther away lies a structure that is far more mysterious: the Oort Cloud. This enormous spherical cloud of icy objects may extend 50,000 to 100,000 astronomical units from the Sun. That is nearly a quarter of the distance to the nearest star. Unlike the Kuiper belt, which forms a flattened disk, the Oort cloud surrounds the solar system in all directions. It is thought to contain trillions of icy bodies left over from the earliest days of planet formation. Most of these objects orbit the Sun extremely slowly. Some take millions of years to complete a single orbit. Normally, they remain undisturbed in the dark outskirts of the solar system, but occasionally something changes their paths. Nearby stars passing through the galaxy can gravitationally disturb these objects. So can giant molecular clouds drifting through interstellar space. And sometimes, the gravitational influence of the planets themselves plays a role. Jupiter's role in controlling comets. Among all the planets, Jupiter has the strongest influence on comets entering the inner solar system. Because Jupiter is so massive, its gravity acts like a giant gatekeeper. As comets approach the inner solar system, Jupiter often intercepts them. Some are captured into shorter orbits around the Sun. Others are completely ejected from the solar system, flung into interstellar space. And occasionally, a comet collides directly with Jupiter itself. One of the most dramatic examples occurred in 1994, when the comet Shoemaker-Levy 9 crashed into Jupiter. Astronomers watched as fragments of the comet slammed into the planet's atmosphere. Each impact released enormous explosions. Some of the scars left behind were larger than Earth. If those fragments had struck our planet instead, the consequences could have been catastrophic. Events like this demonstrate Jupiter's role as a kind of cosmic shield. Its gravity intercepts many dangerous objects before they reach the inner planets. What happens without Jupiter? Now imagine the solar system without Jupiter. That enormous gravitational gatekeeper is suddenly gone. The balance that has existed for billions of years begins to change. Comets entering the inner solar system would no longer encounter Jupiter's powerful gravitational pull. Instead of being deflected or captured, many of them could continue traveling inward. Over millions of years, this could significantly increase the number of comets passing through the inner solar system. Some of these comets would cross the orbits of Mars, Earth, and Venus, and occasionally collisions could occur. Comets are not small objects. Many contain enough energy to cause global devastation. When a large comet strikes a planet, the energy released can equal millions of nuclear explosions. Such impacts can produce enormous shock waves, global fires, and massive climate disruptions. Without Jupiter acting as a gravitational barrier, the inner solar system could become a far more dangerous place. Datuin, a more active inner solar system. Over time, the number of comets entering the inner solar system might slowly increase. Some would pass harmlessly by the planets. Others might break apart as they approach the Sun, creating spectacular comet tails visible from Earth. But a small fraction could collide with planets. Earth itself has experienced comet impacts many times in its history. Some scientists believe that comets may have delivered a portion of the water found in Earth's oceans billions of years ago. But large impacts can also cause devastation. The extinction event that wiped out the dinosaurs was caused by a massive asteroid. A large comet could produce similar effects. Without Jupiter's protective influence, the probability of such impacts might gradually increase. The star dissect. Jupiter as a comet sculptor. Interestingly, Jupiter does not only block comets, it also shapes their orbits. Many short-period comets, those that return to the inner solar system every few decades, owe their paths to Jupiter's gravity. These objects are known as Jupiter family comets. Jupiter captures them into stable orbits that repeatedly bring them close to the Sun. Without Jupiter, many of these comets would follow very different paths. Some might drift outward into deep space. Others might plunge toward the Sun and disintegrate. The population of comets we observe today would look very different. The solar system without its giant. The disappearance of Jupiter would not cause an immediate catastrophe, but over millions of years, the long-term effects could reshape the solar system. More comets might wander inward. Planetary impact rates could slowly increase. And the delicate gravitational structure that has existed for billions of years would begin to evolve in new ways. But comets and asteroids are only part of the story. Jupiter's gravity also plays a crucial role in maintaining the stability of the planets themselves. The giant planet influences the orbits of Saturn, Uranus, Neptune, and even the inner planets. Without Jupiter, those gravitational relationships could begin to change. And over extremely long timescales, the entire architecture of the solar system might begin to shift. In the next chapter, we will explore how Jupiter stabilizes the motion of planets and what might happen if that stabilizing force suddenly vanished. The planetary balance. Beyond the asteroids and comets, Jupiter plays an even more profound role in the solar system. It helps maintain the gravitational balance of the planets themselves. Every planet in the solar system pulls on every other planet through gravity. These gravitational interactions create a complex network of forces. Normally, these forces balance each other out, allowing the planets to remain in stable orbits around the Sun. But because Jupiter is so massive, its gravitational influence is far greater than that of any other planet. In fact, after the Sun, Jupiter is the dominant gravitational force in the entire solar system. Remove Jupiter, and the balance that has existed for billions of years would begin to change. The dance of the planets. The planets do not simply orbit the Sun in isolation. They interact with one another in subtle but important ways. Over long periods of time, these interactions cause slight changes in planetary orbits. Astronomers call these changes orbital perturbations. Normally, these perturbations are small, but when large gravitational bodies are involved, the effects can accumulate over millions of years. Jupiter plays a crucial role in moderating these interactions. Its gravity stabilizes the orbits of several outer planets, particularly Saturn. Together, Jupiter and Saturn form a powerful gravitational pair. Their combined influence shapes much of the architecture of the outer solar system. The Jupiter-Saturn relationship. Jupiter and Saturn are the two largest planets in the solar system. They orbit the Sun in a gravitational relationship known as a resonance cycle. While they are not locked in a perfect resonance, their orbits interact in predictable ways. Over long timescales, these interactions help regulate the distribution of gravitational energy among the planets. This helps prevent the orbits of the outer planets from drifting into unstable configurations. If Jupiter suddenly disappeared, Saturn would immediately become the most massive planet remaining. Without Jupiter's gravitational influence, Saturn's orbit would slowly begin to shift. The changes might be small at first, but over millions of years the cumulative effects could become significant. Saturn could migrate slightly inward or outward, and because Saturn itself influences other planets, these changes would ripple through the solar system. Uranus and Neptune. The outermost giant planets, Uranus and Neptune, would also feel the consequences. Both of these planets interact gravitationally with Saturn and indirectly with Jupiter. The giant planets form a delicate gravitational system. Remove one major component, and the system begins to adjust. Computer simulations of planetary systems show that removing a giant planet can produce unpredictable long-term effects. Some planetary orbits may slowly drift. Others may become more elliptical. In extreme cases, planets can even be ejected from their solar systems entirely. While such dramatic outcomes would likely take billions of years, the absence of Jupiter would certainly alter the long-term evolution of planetary motion. The inner planets, even the inner planets, Mercury, Venus, Earth, and Mars, are indirectly influenced by Jupiter. Although Jupiter lies hundreds of millions of kilometers away, its gravitational reach is enormous. Subtle gravitational interactions ripple through the solar system like waves. These interactions help maintain the long-term stability of planetary orbits. For example, Jupiter slightly influences the orbit of Mars. Mars, in turn, influences Earth. And Earth interacts gravitationally with Venus and Mercury. This chain of interactions connects every planet. If Jupiter vanished, the gravitational balance would shift slightly. Over very long timescales, this could alter the orbital patterns of the inner planets. The changes would not happen quickly, but over hundreds of millions or billions of years, planetary orbits could slowly drift. Sakak, Mercury's unstable orbit. Interestingly, even with Jupiter present, the solar system is not perfectly stable. Modern simulations show that the orbit of Mercury is slightly chaotic over extremely long timescales. Tiny gravitational disturbances can slowly accumulate. Given enough time, perhaps billions of years, Mercury's orbit could become highly elliptical. In rare scenarios, Mercury could even collide with Venus or fall into the Sun. Jupiter's gravitational presence influences these dynamics. Without Jupiter, the long-term evolution of Mercury's orbit could change. Some simulations suggest that removing Jupiter might actually reduce certain orbital instabilities, but other interactions might grow stronger. The overall outcome remains uncertain. The solar system is an incredibly complex gravitational system. Even small changes can lead to very different outcomes over billions of years. Planetary migration. Another possibility involves planetary migration. In many planetary systems discovered around other stars, giant planets migrate inward or outward during their formation. These migrations can dramatically reshape planetary systems. Jupiter itself may have migrated slightly during the early history of the solar system. Some models suggest that Jupiter initially moved closer to the Sun before reversing direction due to interactions with Saturn. This event, known as the Grand Tack hypothesis, may have played a key role in shaping the distribution of rocky planets. Without Jupiter's gravitational influence today, the long-term motion of planets might slowly evolve in new ways. Saturn could shift slightly. This could influence Uranus and Neptune. And, over immense timescales, even the inner planets might experience subtle changes in their orbital patterns. A solar system. Slowly changing, the disappearance of Jupiter would not immediately destabilize the solar system. The planets would continue orbiting the Sun, much as they do today. But the long-term gravitational evolution would begin to diverge from its current path. Over millions of years, planetary orbits could slowly drift. Over hundreds of millions of years, the cumulative effects might become more noticeable. And over billions of years, the architecture of the solar system could look quite different. Jupiter's absence would remove one of the major stabilizing forces in the system. The result would be a solar system gradually evolving along a new and uncertain trajectory. The final question. Despite all these possibilities, one mystery remains. Would life on Earth still exist if Jupiter had never formed? Some scientists believe Jupiter's gravitational influence helped protect the early Earth from frequent catastrophic impacts. Others argue that Jupiter may have actually increased the number of objects entering the inner solar system during certain periods. The truth may lie somewhere in between, but one thing is certain. Jupiter has played a major role in shaping the environment in which Earth and life itself developed. Without Jupiter, the story of our solar system might have unfolded very differently. And in the final chapter, we will explore the ultimate question: how Jupiter may have influenced the history of life on Earth itself, and whether our planet might exist in its current form if the solar system's giant guardian had never been there at all. Earth without Jupiter. After exploring asteroids, comets, and the motion of planets, one final question remains, perhaps the most important question of all. What would Earth be like if Jupiter had never existed? Would life still have appeared on our planet? Would Earth even be here today? To answer this, scientists must look back billions of years to the earliest days of the solar system, a time when planets were still forming and space was filled with countless fragments of rock and ice. This chaotic period is known as the Late Heavy Bombardment, the violent early solar system. About 4 billion years ago, the young solar system was far more dangerous than it is today. Millions of asteroids and comets traveled through space on unstable paths. Many of these objects frequently collided with the inner planets. Evidence of this violent period can still be seen on the Moon. Its surface is covered with enormous craters created by ancient impacts. Earth was bombarded as well, but because our planet has oceans, weather, and plate tectonics, most of those ancient scars have been erased. These impacts played an important role in shaping the early Earth. Some scientists believe that comets delivered water and organic molecules to the young planet. These ingredients may have helped create the conditions necessary for life to emerge. But at the same time, large impacts could also cause mass destruction. A collision with a sufficiently large asteroid could sterilize large portions of a planet's surface. Jupiter's protective role. Jupiter may have acted as a protective barrier during this dangerous time. Because of its enormous gravity, Jupiter can capture or deflect many incoming objects. Some asteroids are pulled toward Jupiter and collide with the giant planet, instead of continuing toward the inner solar system. Others are flung completely out of the solar system. In this way, Jupiter may have reduced the number of large impacts reaching Earth over billions of years. The famous Shoemaker-Levy 9 collision in 1994 demonstrated this protective effect. The comet fragments that struck Jupiter would have caused catastrophic destruction if they had hit Earth instead. Jupiter essentially absorbed the impact on behalf of the inner planets. But the story is more complicated than simply calling Jupiter Earth's protector. Jupiter, protector or threat? Some scientists argue that Jupiter's gravitational influence may also send objects toward Earth. By disturbing the orbits of asteroids and comets, Jupiter can sometimes redirect them into the inner solar system. This means Jupiter may both protect and threaten Earth at the same time. Computer simulations suggest that Jupiter plays a complex role in controlling the flow of objects through the solar system. Without Jupiter, some dangerous comets might never be redirected toward Earth. But without Jupiter's gravitational barrier, other objects might travel inward more easily. In other words, Jupiter may regulate the number of impacts Earth experiences rather than simply preventing them, and that balance may be extremely important. Too many impacts. If the inner solar system experienced too many large impacts, life might never have had time to evolve. Massive collisions could repeatedly reset the development of complex organisms. Entire ecosystems could be wiped out again and again. Early life on Earth may have required long periods of stability in order to evolve. Without Jupiter helping regulate incoming objects, the impact rate might have been much higher. Frequent global catastrophes could have prevented complex life from developing. In this scenario, Earth might remain a barren world dominated only by microbial life. Too few impacts. But impacts are not always destructive. They can also deliver important materials. Many scientists believe that water may have arrived on Earth through impacts with icy bodies. Organic molecules delivered by comets and asteroids may have helped trigger the chemical reactions that eventually produced life. If Jupiter had prevented too many of these impacts, Earth might have remained dry. Without enough water, our planet might never have developed oceans. And without oceans, life as we know it would be far less likely. So Jupiter's role may have been to maintain a delicate balance, enough impacts to deliver essential ingredients, but not so many that life was constantly destroyed. A rare planetary system. When astronomers began discovering planets around other stars in the 1990s, they found something surprising. Many planetary systems look very different from our own. In many cases, giant planets orbit extremely close to their stars. These planets are known as hot Jupiters. Their powerful gravity can disrupt the formation of rocky planets like Earth. In some systems, giant planets migrate inward and scatter smaller planets out of stable orbits. These discoveries suggest that our solar system's structure may be somewhat unusual. The presence of a giant planet like Jupiter in a distant orbit may help create stable environments for habitable worlds. If this idea is correct, Jupiter-like planets might play an important role in the development of life. The solar system today. Today, Jupiter continues to influence the solar system. Its gravity still controls the motion of countless asteroids. It continues to capture or redirect comets. Its moons remain fascinating worlds where scientists search for signs of alien life. And its enormous mass helps maintain the gravitational balance of the planetary system. Jupiter is more than just a planet. It is one of the key architects of our cosmic neighborhood. The final thought: if Jupiter suddenly disappeared tomorrow, the solar system would not collapse overnight. The planets would continue orbiting the Sun. Earth would continue spinning beneath its blue skies. But over millions and billions of years, the absence of Jupiter would gradually reshape the solar system. Asteroids would drift into new paths. Comets might enter the inner solar system more frequently. Planetary orbits could slowly evolve. And the delicate gravitational architecture that has existed for billions of years would slowly change. In many ways, Jupiter is like the quiet giant of our solar system, a massive world whose influence stretches across billions of kilometers, shaping the motion of planets, guiding comets and asteroids, and perhaps even helping create the conditions that allowed life to appear on Earth. The next time you look up at the night sky, remember that somewhere out there, far beyond the bright stars, is a giant planet quietly protecting and shaping our cosmic home. Without Jupiter, the story of Earth, and perhaps life itself, might have been very different. The solar system in the far future. Now imagine that Jupiter truly disappeared, not in a distant past, but suddenly, today. At first, almost nothing would seem to change. The sun would still shine. The planets would continue their journeys around it. Earth would keep spinning, carrying oceans, clouds, and life through space, just as it has for billions of years. But hidden within the gravitational fabric of the solar system, subtle changes would already be beginning. Changes that would slowly unfold over thousands, millions, and eventually billions of years. Because Jupiter is not just a planet, it is one of the primary gravitational anchors of our solar system. Remove it, and the long-term future of the planetary system could begin to diverge from the path it has followed since its birth. The first few thousand years. During the first centuries after Jupiter vanished, the solar system would appear almost identical to what we see today. The planets would remain in nearly the same orbits. Astronomers observing the sky from Earth would still see Mars glowing red. Saturn would still display its magnificent rings. Neptune and Uranus would continue their distant journeys through the darkness of the outer solar system. But computer simulations show that even tiny gravitational shifts can slowly accumulate over time, and Jupiter's gravity currently provides constant small corrections to planetary motion. Without those corrections, planetary orbits would begin evolving in slightly different ways. The differences would be tiny at first, almost impossible to detect, but over long timescales, those small differences could grow. Navaja. Millions of years later, after millions of years, the solar system could begin to show measurable changes. The asteroid belt would likely look different. Without Jupiter maintaining its resonances, asteroids could slowly drift into new regions of space. Some would migrate inward. Others might collide and merge. Gradually, the structure of the belt could evolve into something very different from what we see today. At the same time, comet activity in the inner solar system might slowly increase. Without Jupiter ejecting many incoming comets, more of them could reach the inner planets. Most would pass harmlessly through the solar system. But a few might collide with planets. Impact rates on Earth could slowly increase over long timescales. Still, these changes would happen slowly. Civilizations rising and falling on Earth might never even notice them. Hundreds of millions of years. Now imagine the solar system hundreds of millions of years in the future. Gravitational interactions between the remaining planets would continue evolving. Saturn, now the largest planet, would become the dominant gravitational force beyond Mars. But Saturn is far less massive than Jupiter. Its influence would not be strong enough to stabilize the outer solar system in quite the same way. Over extremely long periods, the orbits of Uranus and Neptune might slowly drift. Planetary resonances could change. Small orbital variations might grow larger over time. In most scenarios, the solar system would remain stable. But in rare cases, computer simulations suggest something more dramatic could occur. Planetary orbits might become chaotic. And if that happened, collisions between planets, though incredibly unlikely, could eventually become possible over billions of years. The long-term chaos of planetary systems astronomers studying planetary systems around other stars have discovered something surprising. Many planetary systems are not stable forever. Planets sometimes migrate inward. Others are flung outward into interstellar space. Some collide with one another. Others spiral into their stars. These chaotic outcomes occur because gravitational interactions between planets can amplify over time. Our solar system has remained stable for billions of years, partly because of its current configuration. Jupiter's presence plays an important role in that stability. Without it, the long-term evolution of the system could follow a slightly more chaotic path. Still, even in the absence of Jupiter, the solar system would likely remain stable for billions of years. The Sun itself would become the dominant force shaping its future. The Sun's final evolution. Long before planetary chaos could destroy the solar system, another event will occur: the death of the Sun. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core. It will begin expanding into a red giant star. As the Sun grows larger, it will swallow the inner planets. Mercury and Venus will certainly be destroyed. Earth may also be consumed, or its surface may be scorched into a lifeless desert. The outer planets, including Saturn, Uranus, and Neptune, will survive this transformation. But their orbits will slowly expand as the Sun loses mass. Eventually, the Sun will shed its outer layers into space, creating a glowing, planetary nebula. At its center will remain a dense stellar remnant called a white dwarf. By that time, the solar system will be completely transformed, and whether Jupiter exists or not will hardly matter. The legacy of Jupiter. Even though Jupiter might someday disappear in our thought experiment, its influence on the solar system would never truly vanish. For billions of years, Jupiter has shaped the architecture of our planetary neighborhood. It helped sculpt the asteroid belt. It redirected countless comets. It influenced the orbits of planets. And it may have played a role in protecting Earth during the fragile early stages of life's evolution. Jupiter is not simply a giant planet. It is one of the main forces that shaped the solar system we live in today. The cosmic perspective. When we imagine Jupiter disappearing, we're really exploring something deeper. The delicate balance that allows planetary systems to exist, the gravitational dance that keeps planets in stable orbits, and the cosmic conditions that make life possible. Across the galaxy, billions of planetary systems exist. Some may have giant planets like Jupiter, others may not. Some may host habitable worlds, others may remain barren. Understanding Jupiter's role helps scientists understand what kinds of planetary systems might support life elsewhere in the universe. The final reflection. In the end, Jupiter reminds us how interconnected the universe truly is. A planet hundreds of millions of kilometers away can influence the fate of worlds closer to the Sun. A giant sphere of gas can shape the history of asteroids, comets, and perhaps even life itself. The solar system is not a random collection of planets. It is a carefully balanced gravitational system, a cosmic clockwork shaped by forces acting over billions of years. And somewhere within that vast structure, Jupiter stands as one of its most powerful architects, quietly guiding the motion of worlds, while orbiting the Sun in the cold darkness of space. A silent giant whose presence has shaped the story of our cosmic home. Could another Jupiter exist? If Jupiter vanished today, the solar system would eventually adapt to its absence. But this raises another fascinating question. Could another planet ever replace Jupiter? Could a new giant world form somewhere in our solar system and take over its role? To answer that, we need to understand how Jupiter formed in the first place, because Jupiter's birth was not a simple event. It was one of the most dramatic processes in the early history of the solar system, and it happened at a very specific moment, when the young Sun was surrounded by a vast disk of gas and dust, the birthplace of giant planets. Around 4.6 billion years ago, our solar system looked nothing like it does today. There were no clear planetary orbits, no calm asteroid belt, no stable arrangement of planets. Instead, the young Sun was surrounded by a massive protoplanetary disk, a swirling cloud of gas, dust, and icy material. Inside this disk, countless small particles began colliding and sticking together. Over time, these particles formed larger and larger bodies. Pebbles became rocks. Rocks became planetesimals. Planetesimals became planetary embryos. In the outer regions of the disk, where temperatures were extremely low, ice could form easily. This allowed planets to grow much larger than the rocky worlds closer to the Sun. And somewhere beyond the young asteroid belt, a massive core began to form. This core would eventually become Jupiter. The core accretion process. Scientists believe Jupiter began as a rocky and icy core, roughly 10 times the mass of Earth. Once this core became large enough, its gravity started attracting enormous amounts of gas from the surrounding disk. Hydrogen and helium, the same elements that make up the Sun, began falling toward the growing planet. At this point, Jupiter's growth accelerated dramatically. Within a relatively short cosmic time, the planet captured huge quantities of gas. Its mass expanded rapidly, and eventually, Jupiter became the enormous gas giant we see today. But this process could only occur while the protoplanetary disk still existed. Once the gas in the disk disappeared, giant planet formation became nearly impossible. The missing ingredients. Today, the solar system no longer contains the raw materials needed to form another Jupiter. The gas that once filled the protoplanetary disk vanished billions of years ago. Most of it was blown away by the young sun's powerful radiation. Some was captured by the giant planets themselves. Without that massive reservoir of hydrogen and helium, new gas giants cannot form. Even if rocky cores continued to grow in the outer solar system, they would never accumulate the enormous gaseous envelopes that define planets like Jupiter and Saturn. In other words, Jupiter could never be replaced. Its formation required conditions that existed only during the earliest chapter of the solar system's history. A giant that arrived early. In fact, Jupiter may have formed extremely early. Some studies suggest it began forming within the first million years after the Sun was born. This early formation allowed Jupiter to strongly influence the evolution of the entire solar system. Its gravity may have shaped the structure of the asteroid belt. It may have limited the growth of Mars, and it may have prevented large amounts of material from reaching the inner solar system. Some scientists even propose that Jupiter migrated slightly during its early formation. A theory known as the Grand Tack model suggests Jupiter may have moved inward toward the Sun before reversing direction and moving outward again. This migration could explain why the inner solar system contains relatively small planets compared to the giant worlds farther away. Jupiter's moons, a mini solar system. While Jupiter itself cannot be replaced, it has created something remarkable of its own, a miniature planetary system. Jupiter has more than 90 known moons. Many of them are small and irregular, but 4 of them are enormous and scientifically fascinating. These moons are known as the Galilean moons, discovered by Galileo Galilei in 1610. They are Io, Europa, Ganymede, Callisto. Each of these worlds is unique. Io is the most volcanically active world in the solar system. Europa hides a vast ocean beneath its icy crust. Ganymede is the largest moon in the entire solar system, even larger than the planet Mercury. And Callisto preserves one of the oldest cratered surfaces known. Together, these moons form a complex gravitational system orbiting Jupiter. The search for life around Jupiter. Among Jupiter's moons, Europa has become one of the most intriguing targets in the search for extraterrestrial life. Beneath its thick ice shell lies a global ocean of liquid water. This ocean may contain more water than all of Earth's oceans combined. Scientists believe tidal forces from Jupiter's gravity heat Europa's interior. This heat may create hydrothermal vents on the ocean floor, similar to environments where life thrives on Earth. Future missions, such as NASA's Europa Clipper, aim to study this ocean in greater detail. If life exists anywhere else in the solar system, Europa could be one of the most promising places to find it. In this way, Jupiter may not only influence Earth's history, it may also host environments where life could exist elsewhere. Taxis, giant planets across the galaxy. When astronomers search for planets around other stars, they often find giant planets similar to Jupiter. Some orbit far from their stars, others orbit incredibly close. These discoveries show that giant planets are common in the universe, but their positions vary greatly. In some planetary systems, giant planets migrate inward and destroy smaller, rocky planets. In others, they stabilize the system in ways similar to Jupiter's role here. Studying Jupiter helps astronomers understand how planetary systems form across the galaxy. It provides a blueprint for understanding how giant planets shape the architecture of their systems. A unique giant. Even among gas giants, Jupiter is extraordinary. It is more massive than all the other planets combined. Its magnetic field is incredibly powerful. Its storms can last for centuries. The most famous of these storms is the Great Red Spot, a gigantic hurricane larger than Earth that has raged for more than 300 years. Jupiter rotates extremely quickly as well. A full day on Jupiter lasts less than 10 hours. This rapid rotation helps generate powerful atmospheric bands and storms. Despite being made mostly of gas, Jupiter behaves almost like a failed star. In fact, if Jupiter were about 80 times more massive, it could ignite nuclear fusion and become a small star known as a brown dwarf, the giant that cannot be replaced. In the end, Jupiter represents something truly unique. It formed during a brief window in cosmic history. It shaped the evolution of the solar system. It continues influencing the motion of countless objects even today. And if it were ever removed from the solar system, no new planet could take its place. The conditions that created Jupiter vanished billions of years ago. What remains is a giant world that continues orbiting the Sun, quietly shaping the cosmic neighborhood around it. A reminder that even a single planet can influence the fate of an entire planetary system, and perhaps the fate of life itself. The solar system without its silent giant. Throughout this documentary, we explored a simple but powerful question. What would happen if Jupiter suddenly disappeared? At first glance, the idea might seem harmless. After all, Jupiter is far away, nearly 780 million kilometers from Earth. It does not warm our skies like the Sun. It does not shine brightly like Venus. It does not influence our tides like the Moon. And yet, despite its distance, Jupiter quietly shapes the fate of the entire solar system. It is not just another planet. It is a gravitational giant whose influence stretches across billions of kilometers. And without it, the story of our cosmic neighborhood might look very different. A planet that holds the system together. Jupiter's most important role is something we rarely notice. Stability. The solar system is not a static structure. It is a constantly shifting gravitational dance. Every planet pulls on every other planet. Every asteroid is influenced by the gravity of multiple worlds. Even the smallest changes can ripple across millions of kilometers of space. Jupiter acts like a massive anchor in this gravitational system. Its enormous mass stabilizes the orbits of many objects across the solar system. The asteroid belt, for example, exists partly because of Jupiter's influence. Without Jupiter, the belt might never have formed the way it did. Instead of remaining in a distant ring between Mars and Jupiter, many asteroids might have migrated toward the inner planets. Some could have collided with Earth long ago. Others might have altered the formation of the rocky planets entirely. In this sense, Jupiter helped shape the environment in which Earth was born. The guardian of the inner planets. For decades, scientists have debated whether Jupiter truly acts as a cosmic shield. The idea is simple. Because Jupiter is so massive, it intercepts many incoming objects, especially comets from the outer solar system. When these icy bodies fall toward the Sun, Jupiter's gravity often pulls them off course. Some are captured into new orbits. Others are flung out of the solar system entirely. And sometimes, Jupiter itself takes the impact. The collision of comet Shoemaker-Levy 9 in 1994 gave us a dramatic example of this process. Fragments of the comet slammed into Jupiter at incredible speeds. The explosions released more energy than the largest nuclear weapons ever built. Dark scars appeared in Jupiter's atmosphere, some larger than Earth itself. If even one of those fragments had struck our planet, the consequences would have been catastrophic. Moments like that remind us that Jupiter is not simply a distant gas giant. It is a world constantly interacting with the debris of the solar system, and in doing so, it may help protect the inner planets from some of the most dangerous objects wandering through space. The delicate balance of impacts. But Jupiter's role is more complex than simply acting as a shield. In some situations, its gravity can actually send objects toward Earth. By disturbing the orbits of asteroids and comets, Jupiter sometimes redirects them into the inner solar system. This means Jupiter may both increase and decrease impact risks at different times. What matters most is balance. Without Jupiter, the flow of comets into the inner solar system might change dramatically. Some objects that would normally be ejected might continue inward. Others might never be redirected toward Earth at all. The result could be a very different pattern of impacts across billions of years. And those impacts played an important role in Earth's history. They delivered water. They delivered organic molecules. They reshaped ecosystems, and at least once, they caused a mass extinction that changed the course of life. Akuhord, Jupiter and the birth of Earth. The influence of Jupiter may go back to the earliest days of the solar system. Some scientists believe Jupiter helped shape the formation of the inner planets. Its powerful gravity may have prevented too much material from reaching Mars. This could explain why Mars is much smaller than Earth and Venus. The presence of Jupiter may also have helped define the boundary between the rocky inner planets and the gas giants beyond. Without Jupiter forming when it did, the solar system might have developed in a completely different way. Perhaps the inner planets would have been larger, perhaps smaller. Or perhaps Earth would never have formed at all. The presence of a giant planet at the right distance from the Sun may have been one of the key ingredients that allowed our world to exist. A rare planetary architecture. When astronomers began discovering planets around other stars, they expected many systems to look like ours. Instead, they found something surprising. Many planetary systems contain giant planets extremely close to their stars. These worlds, known as hot Jupiters, orbit their stars in just a few days. Their gravity can disrupt the formation of smaller rocky planets. Some systems appear chaotic. Others contain planets with wildly eccentric orbits. Compared to these strange planetary systems, our solar system appears unusually orderly. The presence of Jupiter in a distant orbit may be one of the reasons for that stability. A giant planet positioned far from the Sun can help shape the structure of the entire system without destroying the inner worlds. If that idea is correct, Jupiter-like planets may be important ingredients for habitable planetary systems throughout the galaxy. The silent giant. Despite its enormous influence, Jupiter remains a mysterious world. Its thick clouds hide the deep interior beneath. Its atmosphere is filled with storms larger than entire planets. Its magnetic field is the strongest of any planet in the solar system, and its moons may contain some of the most promising environments for life beyond Earth. The giant planet continues to teach scientists about planetary physics, atmospheric chemistry, and the formation of solar systems. Spacecraft, such as NASA's Juno mission, are currently studying Jupiter in remarkable detail. With every orbit, Juno reveals new information about the planet's structure, magnetic field, and atmosphere. Even after centuries of observation, Jupiter still holds many secrets. Looking back at the thought experiment. So what would truly happen if Jupiter disappeared? Not tomorrow, not suddenly. But if it had never existed at all, the solar system might still contain planets. The sun would still shine. But the delicate gravitational structure we see today could be very different. Asteroid paths might shift. Comet traffic might change. Planetary orbits might slowly evolve over millions of years, and, perhaps most importantly, the history of Earth itself might have unfolded along a very different path. Life might have struggled to emerge, or perhaps it would have flourished even more easily. We cannot know for certain. But exploring these possibilities helps scientists understand how planetary systems truly work. A cosmic reminder. Jupiter reminds us that the universe is deeply interconnected. Even a planet hundreds of millions of kilometers away can influence the destiny of worlds closer to the Sun. Gravity binds everything together, from the smallest asteroid to the largest star. Each object shapes the motion of others in subtle ways. And over billions of years, those tiny influences build the cosmic structures we see today. End of documentary.